This blue slide is longer than the straight yellow one, and the ball still reaches the bottom first. Same starting point, same finish, same gravity, no pushing, no friction, no tiny engine hidden in the blue ball. Watch them again. The yellow ball takes the shortest route while the blue ball drops hard, swings underneath it, and wins by a frankly rude amount. The blue curve is called a cycloid, and I'm withholding why it wins for a minute, because the reason is much stranger than steep things go fast. Plenty of steep curves lose. Plenty of short curves lose too. Somehow this particular shape balances two things that fight each other, getting speed early and avoiding extra distance later. I got this wrong the first time because I assumed a circular arc had to be best. It looks smooth, it starts steep, and circles usually show up whenever geometry wants applause. But the circle loses too. So here's the actual challenge. Connect these two dots with any slide you want. Gravity gets one ball from the first dot to the second. Which shape gives the smallest time? Keep your eye on the blue ball, because the clue is hiding in where it earns its lead. The blue ball earns almost all of its lead right here, in the first drop. Once an object has fallen through a vertical height, h, its speed is the square root of 2gh. The route it took to lose that height doesn't matter. Gravity keeps extremely simple receipts. So near the top, the straight slide is in trouble. It descends gently, which means its ball stays slow during the exact part of the trip where every sluggish second is expensive. The blue slide spends extra distance dropping almost vertically. That sounds wasteful until you notice what it buys. Speed that can be used for the entire remaining trip. Imagine two errands. One route makes you walk directly toward the store. The other sends you sideways to grab a bicycle, then lets you ride. The bicycle route can be longer and still win. Here, height is the bicycle shop, but dropping straight down forever obviously fails because eventually you have to reach the finish, which is annoyingly over there. So the fastest path has to turn. The real question is when. Turn too early and you never build enough speed. Turn too late and you scream past the useful part of the map. We need a rule that tells each tiny piece of the track what angle to choose. And weirdly, that rule already exists in a completely different corner of physics. Light knows it. Light solves the same kind of problem. Find the route that takes the least time when speed changes from place to place. Put air above water, and a light ray bends at the boundary. It chooses a longer geometric route, so it can spend less of the trip in the slower material. That sentence still feels like light is doing paperwork, but the mathematics works. The rule is Snell's law. Sine of the angle, divided by speed, stays constant from one layer to the next. Now turn our gravitational world into a stack of very thin horizontal layers. Inside one layer, the ball's speed is nearly constant because its height barely changes. Deeper layers mean larger h, so they also mean larger speed. Our slide becomes a chain of tiny straight segments, each refracting as it crosses into a faster layer. The best angle in every band obeys the same rule as light. Watch what happens as the layers get thinner. The sharp corners soften. The chain settles into one smooth curve, dropping nearly vertically at first, then bending toward the finish as speed grows. And there it is again, the cycloid. This is the screenshot part, by the way. A falling ball and a bending light ray are following the same least time law. One passes through layers of material. The other passes through layers of gravitational speed. Fine, we found a rule that generates the shape, but the computer kept refracting lines until this appeared. Is a little unsatisfying. What actually is a cycloid, and why does it have exactly the right bend? A cycloid is the trail made by one dot on the rim of a rolling wheel. Keep your eye on the pink dot. As the circle rolls, the dot touches the ground, rises, arches forward, and touches down again. Flip one arch upside down and you get our slide. Honestly, I love that the fastest path is hiding in a wheel like this. It feels less invented. For anyone who wants the exact curve, let the wheel rotate through an angle theta. Then x equals a times theta minus sine theta, and y equals a times 1 minus cosine theta. The scale a and the final value of theta are chosen so the arch hits our finish point. The notation is a little ugly, and I'm sorry on behalf of mathematicians. The picture is doing the real work. Near the starting cusp, the curve is vertical. That gives away horizontal distance temporarily and converts height into speed as aggressively as possible. Lower down, the wheel-generated arc flattens, because speed is already plentiful, and the remaining job is reaching the finish without wandering. Every point makes the same local trade. One more bit of distance versus one more bit of early acceleration. Now race it against the best imposters. Straight line, circle, parabola, each can be tuned to the same endpoints. The cycloid still arrives first. That's evidence, though, and a pile of races can't prove nobody has drawn some bizarre squiggle that wins. To rule out every possible curve at once, we need to measure time itself along the track. For one tiny piece of track, time is distance divided by speed. Call the tiny distance d's. At height y below the start, speed is the square root of 2gy. So the total travel time is what you get by adding d's over square root of 2gy along the whole curve. This is an integral, but don't let it put on a little judge's wig and intimidate you. It's just a receipt. Every tiny segment charges for its length, then gives a discount based on how deep and fast the ball already is. Near the top, y is small, so the discount is terrible. Length up there costs a lot of time. Deeper down, the ball is fast and extra distance is cheaper. That single fact explains the cycloid's personality. It refuses to spend distance near the top. It dives. Then it allows itself a wider sweep where motion is cheap. The formal tool for minimizing this receipt is the calculus of variations. Instead of nudging one number, it nudges an entire curve. Give the cycloid a small bump anywhere and the time increases. Pull it inward somewhere else and the time still increases. At the winning curve, all the first order improvements cancel. That condition produces the same sine over speed rule we stole from light, and solving it produces the wheel equations. Two roots to the same answer. Refraction for the intuition, variational calculus for the guarantee. So the cycloid really is fastest. Then the curve does one more thing that feels almost made up. Start balls from different places on it, and they all reach the bottom together. Yep. 3 balls, 3 starting heights, 1 arrival time. Release them together. The low ball has less distance to travel, but it also starts on a gentle part of the curve and gains speed slowly. The high ball travels farther, yet its section is steeper, so it catches up. On a cycloid, those effects balance exactly. This is the Tautochrone property, meaning equal time curve, and it's the same shape, wearing a second ridiculous hat. Watch one dot now. Wherever it starts, its motion toward the bottom behaves like a perfect pendulum's side-to-side motion. The distance parameter changes sinusoidally, which gives every release point the same quarter period to reach the lowest point. Friction ruins this in real life, of course. Air resistance joins in because apparently the universe hates a clean demo, but with ideal rolling or sliding assumptions handled consistently, the timing result survives the mathematics. This also explains why old pendulum clocks briefly flirted with cycloidal guides. A normal pendulum takes almost the same time for small swings, while a cycloidal constraint makes the timing exact across a wider range. So our longer slide wins because it buys speed where time is expensive and spends distance where time is cheap. The wheel-drawn curve balances that exchange at every point. And here's the thing that still bugs me. The same cycloid answers both which route is fastest and which starting points arrive together. Those sound like different questions. The curve apparently disagrees.